All right. Hey guys. Sorry this is late. Again, it's been a crazy week. I swear I'm going to have a not crazy week at some point. But I will make sure that the quiz, it's going to be extended out till next Tuesday. And then we will take up our regular schedule. Yeah, so everything has gotten a little pushed back, also due to the holiday. All right, so we're going to be talking about probability and randomness. This is kind of a continuation of last week's lecture. So, random variables. A random variable is a variable whose value is a numerical outcome of a random process. So if we think about tossing a coin, a random variable could be the number of heads we get. The random variables we're the most interested in are things like the mean of a random sample. So we're going to talk about two different types of random variables: discrete and continuous. So the first one we'll talk about is discrete. So we've been looking at a lot of probabilities lately, and the examples I've given you follow kind of specific rules. The outcome probabilities must be between 0 and 1, and if you add them all up, they add up to 1. When the outcomes are numerical, they're values of a random variable. These are called discrete random variables. So you can think of it like we're never going to get anything that's not 1, 2, 3, 4, 5. We get very, very specific numbers, successes, failures, let's say dice rolls, things like that. You know, comparing it to continuous would be something like temperature or height, where you're going to get decimals. You're going to get things where you can be as specific as you want to on there. But this is going to be specific integers. So, discrete random variable, we'll call that x, has possible values and probabilities that can be given in an ordered list. You can see here the value of x is up top, x1, x2, and x3, and the probability of each is under that. x1 has probability of p1, x2 has probability of p2, and x3 has probability of p3. The probabilities, which we collectively call pi, must satisfy these rules. Every probability is a number between 0 and 1. You can think of this as like, for instance, heads. If we're looking at a coin, if we say heads is 1 and tails is 2, we say 1 has a 0.5 likelihood and tails has a 0.5 likelihood. Or as we would say as percentages, 50% and 50%. And of course, adding them all up equals 1. If they can't add up to equal 1 or they go over 1, something bad's happened. So an example here. Brent University just posted the grades for its English 101 class. 34% of people in the group received A's, 42% of the people in the group received B's, 18% received C's, 2% received D's, and 4% received F's. So let's choose a student at random. The way we can set up our probability distribution, let's convert it from grades to a number code, where F equals 0, D equals 1, C equals 2, etc., etc. Now our grade is a 5-point scale. And obviously, alphanumeric grades, A, B, C, they're very specific. You can only have an A, B, C, D, or F. Or in this case, 0, 1, 2, 3, and 4. And the nice thing about this whole probability is a lot of times you can just add it up. So if we want to find the probability that someone got a B or better, or the probability of x is greater than or equal to 3, all we have to do is add up the probability of x equals 3 and the probability that x equals 4. Or in this case, 0.42 plus 0.34. With that, we get 0.76, or there's a 76% likelihood that someone got a B or better in the class. All right, so continuous random variables is up next. So we're little happy integers there, zeros, 1s, 2s, 3s, and 4s, but a lot of things in the world don't follow that. Things like height, time, weight, temperature, all these don't follow nicely into those little boxes, those little categories. So continuous variables are variables who use an entire range of numbers. If we want to do it as a sample space, you can see S equals all numbers of X, so that X is greater than 0, but less than 1. So, figuring out the probability of X equaling 0.2 can be easy, if we have a specific point. But what if we need to figure out the probability of X is less than 0.3? That's a little bit weirder. So this is when we use our normal density curve, or as we referred to earlier, the z-score. A little review on how to do the z-score, but I have complete faith in you guys to remember this. So first, find the z-score using the formula. Z equals x minus mu over that little sideways 9. I forget the name of that. Or to put it in normal speak, take the score you're given, subtract the population mean, and then divide it by the population standard deviation. Whatever number we get there, we're then going to go find a z-score table, which is super easy to find. You don't have to still hold on to the one from last semester. All you have to do is just find, Google z-score table, and then compare your score to the probability distribution. Lastly, the really tricky part, making sure that you do this. The z-score is giving you the probability of that percent and everything to the left of it. So if you've got a z-score of 2, that means that you're getting the probability of a 2 or below. So if the question says at most, at most 25% of the population does this, we're good. That makes sense because it's everything to the left of 25%. If it says at least, you'll need to take 1 and subtract that z-score from it. That way, we reverse it. We send that curve to the right instead of to the left. And now we find everything at that point and to the right. Next, mean of a random variable. Of course, y'all already know how to do a mean. You add everything up, and then you divide by the number of observations. Finding a mean of the probability distribution is a little different, but it's still fairly easy. All you need to do is take your numerical values, multiply them by their probability, and add them up. Put this in mathematical notation. That would be mu of x equals x of 1 times probability of 1 plus x of 2 times probability of 2 times x of 3, plus x of 3 times probability of 3, plus etc., etc. Remember here that this is going to be for discrete values. This is going to be pretty much impossible to do with continuous. So equally likely variables, or equally likely values, that's going to be pretty easy. All we have to do here is add up the values and multiply by the probability. So let's look at the average roll on a dice, or on a die. Obviously, the probability of getting any one roll is 1/6. So if we write it all out, we get this really long equation. Obviously, we can just compact that down. If we add 1 plus 2 plus 3 plus 4 plus 5 plus 6, then we get 21. So anytime you have equally likely probabilities, all you have to do is add up the values and then times it by the probability. In this case, 21 times 1/6, we know the average roll on a die is 3.5. So somewhere in between 3 and 4. I know it doesn't really necessarily make sense if we're dealing with discrete values, but yeah, that's the mean there. Probabilities are going to be unequal, and that's going to be the same way. It's just going to take a little bit longer, and we don't get to compact it. So let's take rolling 2 dice. So obviously, rolling 2 dice, the likelihood that we're going to get a number in the middle is a lot more likely than one of the extremes. So you can see here, probability of rolling a 2 is 1/36. Probability of rolling a 3 is 1/18. Probability of rolling a 4 is 1/12. Probability of rolling a 5 is 1/9. Probability of rolling a 6 is 5/36. Probability of rolling a 7th is 1/6, etc., etc. So you can see underneath that, we're just going to multiply all of those out. And then we see the average value of rolling 2 dice is a 7. So it's not going to be particularly easy, but it's at least going to be decently simple. Like I said, continuous means it's going to be very complicated. Oftentimes, you'll need to either use a computer software or, advanced mathematicians have their own little calculation matrix thing. So we won't be covering that here. Next, we'll talk about statistical estimation. So this is really, really important to get. So this is when we're starting to deal with those values and those specific terminologies that will come up again and again. So let's say we want to estimate the mean height of the population of all American women between 18 and 24. When we're dealing with a population mean, we use the mu, the mu. To estimate, we're going to conduct a simple random sample and get a sample of our young women. Let's say 100. So we're going to use this sample mean, which we call x bar, to estimate mu. So our population, that's all the people that our study is relevant for. That's all American women 18 to 24. And then the mean of that population is called the parameter. The way I remember that is P goes with P, population parameter. Our sample is going to be the group that we choose for our study to do the analysis on. So the 100 American women that we choose to do the research on is our sample. And the mean of that sample is called the statistic. Again, S goes with S. So sampling next. So stats obtained from probability samples are considered random variables because their values vary with every sample. If we hopefully we get a representative random sample, our sample mean should be close to our population mean. It's not really perfect, and it'll change if we pull a different sample, but it's a reasonable estimate. If we pick 100 people with, 100 women with the average height, we're going to get somewhere around the average height of the American woman, if we pulled that representative sample. But why? So this is when we kind of start talking about the basis that statistics is based on. The law of large numbers. So the law of large numbers sounds complicated, but it's going to be pretty simple. So as we add more and more observations to our sample, the sample mean or statistic will continue to get closer and closer to the population mean or parameter and will always stay close. It won't just massively deviate here. So that's what's called the law of large numbers, and it holds for just about any population. So thinking about when we were talking about coin flips from last week's lesson, they were incredibly varied in the beginning, right? If we did 5 coin flips, we might have a 70% likelihood of getting heads. But once we start doing 100, 1,000, 10,000, we start getting a lot closer. We start to get really close to that 0.5 probability. So this is kind of a real-life application of, hey, don't go gambling, because in the end, as they say, the house always wins. The casino is always going to make a profit, because while we can't benefit as individuals from the law of large numbers in the casino does. So in gambling, individuals can strike it big and make a decent bit of money once or twice, but the casino, always wins due to the law of large numbers. So every game has bad odds. So if the odds of not winning a blackjack hand is about 58%. The odds of not winning in roulette with the highest likelihood bet, so if you put on your money on red or black, it's not 50-50 because there's also green. So in that case, it's still very subtly weighed against you, because for every 18 red and every 18 18 black spaces, there are 2 greens. So that means no matter what, you are slightly on the side of not likely to win in roulette, even in your most likelihood odds. Slots are even easier because they just straight up program the slots to just make 10% back for them in the long run. So no matter how long you play, no matter how many jackpots you get, the casinos are always going to win money long term. So don't gamble because it's really bad for you and you can ruin your life. So you're always at the worst odds in the house. So when we talk about the law of large numbers, well, how large is large? So it depends on the variability of those outcomes. Outcomes that are much more variable need more trials to ensure the sample mean is close to the distribution mean. So you can think about something like height, right? Height in reality is not that varied. You know, most people are between the heights of what 5.3 or 5'4" and 6'3". That's a pretty narrow range of variability. But gambling is a situation where it's highly variable whether or not you're going to win or lose. You know, your rates of likelihood go all over the place. So that's actually how people get addicted to gambling and ruin themselves financially. It's the fact that you never know when you're going to win. That variability is so high that when you do win, it's amazing. But you never know what's going to happen because that win might be just around the road. And if you walk away now, you may not get that win. So that's why it keeps you at the table. But again, you can never benefit from the law of large numbers. The casino benefits from the law of large numbers and will always get a profit. So yeah, don't gamble. It's bad. If you learn one thing from this, do that. So we've talked about the mean and standard deviation. We've talked about standard deviation before and variance is related to it. So let's go through another review of that. So mean obviously gives us the measure of center. So does median, right? But we also need a measure of spread, how far apart the data is, in order to learn more, in order to simulate that curve. That's what we call the variance and the standard deviation. So you can see those two symbols. The difference between variance and standard deviation is that variance is squared and standard deviation is not. So this is really important to get because variance is important for equations. A lot of statistical equations are going to require you to find the variance to do more. But in real world terms, the standard deviations are good for understanding because, like we said previously, with that whole 68%, 95%, 99.7%, we know, okay, all the data that's going to be between +1 standard deviation and -1 standard deviation is going to be about 68%. So standard deviations are also a lot easier to interpret because they're in regular units, right? If we look at feet, then we can analyze it by feet, you know, in terms of height, not in terms of like number of feet. Variance, you have this weird like squared unit thing. So it's a lot harder to understand. So you're now looking at the data as feet squared. So we have calculated variance and standard deviations before. So a quick reminder, what you do, subtract each data point from the mean and square the difference. Then you add all of them together. So it's basically the same process, except you'll multiply each squared result by the probability. So that'll get you the variance. All right, so the standard deviation is a good bit easier. All you have to do is, once you find the variance, just square root that guy. Like I said, we're only doing this on discrete variables. You have to use some sort of statistical program or use a lot of really advanced math in order to find it for a continuous variable. So an example here. Let's find the mean, variance, and standard deviation of the number, x, of fall courses taken by students at Brent University. So the likelihood of you only taking one course is 6%. The likelihood of you only taking two courses is also 6%. The likelihood of you taking three courses is 12%. The likelihood of you taking four courses, 20%, five courses, 41%, and six courses, 15%. So what we do here is we multiply each number by the likelihood of that number occurring, and you see we get the average is 4.29 classes every semester, or in this fall semester. And to find the variance, we take the individual courses that people have taken, subtract it from the mean, square that, multiply it by the probability. And then we do that for each data point here. There's also software on the internet. You can look up, probability variance calculators, and that will make life easier for you. But make sure you understand the basics of how to get that information first. As long as you understand that, I have no problem with you using those calculators. So we find that the variance is 1.829. So if we square root that to find the standard deviation, that means it is 1.35. So we can see that about 68% of the sample we chose took between, let's say, 6 and 3 courses. So yeah, there you go. That would be your standard deviation. All right, so last thing, variance can be really weird sometimes. So the mean and the variance of a sum of random variables is equal to the sum of the means/variances of each random variable. That sounds like a weird, wizard riddle there, but let's clarify. Basically what this means is if you do an OR, like we were talking about yesterday or last week, we say, okay, what is the odds of this variable or this variable? What's the mean? We just add those together. We can do the exact same thing with the variances. We can only do that though if the variables are independent. That's to say when the variables aren't related to each other, when knowing something about the likelihood of one variable doesn't tell you much about the likelihood of another variable. You can think of it like a Venn diagram if the circles are completely separate from each other. So stuff like correlation of variances, that kind of is getting into the weeds and is super complicated. We won't cover that in this course. Just so you know, going forward, you'll learn some more about that in a future stats. All right, so that's going to be it for this week. I will set the quiz to be due probably I will be having it due next Tuesday, and then starting Monday we'll have another course. So, all right, y'all have a good week.